Welcome to our quick guide on SPI, I2C, and UART. Imagine a dark blue space filled with glowing circuit board lines, setting the stage for a journey into the world of communication protocols. The title SPI versus I2C versus UART fades in, followed by the subtitle Which one to use when. In the corner, a small Raspberry Pi appears, hinting at the practical side of these protocols. This video will help you understand the basics and differences of these essential communication methods, all in a clean, colorful, and cartoon-style animation. Let's dive right in and explore how devices talk to each other. Before we get into the details, let's answer a simple question. What is a communication protocol? Picture two microcontrollers shaking hands, symbolizing a friendly agreement. Devices need a common set of rules to talk to each other. These rules are called protocols. Think of it as a language that both sides understand. For example, a microchip sends data to a sensor using these rules, ensuring the message is clear and received correctly. Communication protocols make sure that devices can exchange information smoothly, no matter who made them. Start with UART, which stands for Universal Asynchronous Receiver Transmitter. Imagine two old-school telephones connected by wire having a direct conversation. In UART, data flows both ways. TX sends data, RX receives it, and vice versa. It's like a phone call where both people can talk and listen at the same time. UART is full duplex, meaning it can send and receive data simultaneously. Simple, using just two wires plus ground, but it only connects two devices at a time. You'll often find UART in GPS modules or Bluetooth connections. For example, an Arduino and an ESP32 can chat using UART with just two wires. Here's a quick summary of UART's key features. It supports full duplex communication with speeds up to 115,200 bits per second. Only two wires are needed, TX and RX plus a ground connection. UART is limited to connecting just two devices, making it simple but not suitable for larger networks. Common examples include GPS modules and Bluetooth devices. This straightforward setup is perfect for direct, point-to-point communication between microcontrollers. See UART in action. Imagine an Arduino and an ESP32 connected with two wires, TX from one goes to RX on the other, and vice versa. This direct link allows them to exchange data quickly and reliably. It's a straightforward setup, ideal for simple projects where only two devices need to communicate. The ground wire ensures both devices share the same reference, preventing errors. UART simplicity is its biggest strength for basic connection. Next up is I2C, or Inter-Integrated Circuit. Picture a Raspberry Pi acting as the master with three slave devices all hanging on the same two wires. This is the shared bus approach. One master controls the conversation and each device has its own unique address. Data travels on the SDA line while the SCL line provides the clock signal. When the master calls out an address, only the matching device responds. This makes I2C perfect for connecting lots of sensors and displays with minimal wiring. Watch as data pulses along the SDA line while the SCL line ticks like a metronome. The master sends out an address, say 0x48, and the matching sensor lights up, ready to communicate. This addressing system allows over 100 devices to share the same bus without confusion. I2C's clever use of addresses and shared lines makes it a favorite for connecting multiple components in compact spaces. Let's break down I2C's main features. It's half duplex, meaning data can only flow in one direction at a time. Speeds range from 100 to 400 kHz, making it faster than UART but not as fast as SPI. Only two wires are needed, SDA for data and SCL for clock plus ground. You can connect over 100 devices, each with its own address. I2C is commonly used for OLED displays and EEPROM memory chips. Here's a practical example. A Raspberry Pi connects to both an OLED display and a temperature sensor using the same two wires. Each device listens for its unique address and responds only when called. This setup saves space and wiring, making I2C ideal for projects with lots of sensors or displays. It's a great way to expand your project without a tangle of cables. Now let's look at SPI, or Serial Peripheral Interface. Imagine a master device connected to a slave using four wires. SPI is all about speed and efficiency. The master sends data out on the MOSI line, receives data back on the MISO line, and uses SLK to keep everything in sync. The CS, or chip select line, tells the slave when to listen. When CS drops, the slave wakes up and gets ready to communicate. SPI is full duplex, allowing data to flow both ways at once. Watch as data zips out on MOSI, returns on MISO, and the SCLK clock ticks rapidly. The CS line drops, activating the slave device. SPI's high speed up to 50 MHz makes it perfect for demanding tasks like reading from SD cards or driving TFT displays. Each slave needs its own CS line, so wiring can get complex with many devices, but the speed is unmatched. Here's a summary of SPI's features. It supports full duplex communication with blazing speeds from 10 to 50 MHz. Four wires are needed, MOSI for data out, MISO for data in, SCLK for clock, and CS for chip select. Each device gets its own CS line, so you can connect multiple devices, but wiring increases. SPI is commonly used for SD cards, analog to digital converters, and TFT display. See SPI in action. A microcontroller connects to an SD card using four wires. The master sends commands and data while the SD card responds instantly. This setup is perfect for high-speed data transfer, like saving photos or logging sensor data. SPI's speed and reliability make it the go-to choice for storage and display tasks. Now that we've covered UART, I2C, and SPI, let's compare them side by side. UART is simple and great for two devices. I2C is perfect for connecting lots of devices with minimal wires. SPI is the fastest, ideal for high-speed data transfers but needs more wires. Each protocol has its strengths and is suited to different tasks. Understanding these differences helps you pick the right one for your project. Choose UART when you need a straightforward point-to-point connection between two devices. It's ideal for simple communication, like linking a microcontroller to a GPS module or Bluetooth chip. UART's simplicity means fewer wires and easy setup, making it perfect for beginners or small projects. I2C shines when you need to connect many devices with just two wires. It's great for projects with multiple sensors, displays, or memory chips. If you're building a weather station or a data logger with lots of components, I2C keeps wiring neat and manageable. Just remember, all devices must have unique addresses. SPI is your go-to for high-speed data transfer. If you need to move lots of data quickly, like writing to an SD card or updating a display, SPI is the best choice. It's also reliable for real-time applications, but keep in mind that each device needs its own chip select line, so wiring can get a bit complex. Let's recap the key differences. UART is simple and direct, I2C is flexible and supports many devices, and SPI is the fastest but needs more wires. Your choice depends on your project's needs, number of devices, speed, and wiring complexity. Knowing these basics will help you design better electronics. Let's clarify an important concept: full duplex versus half duplex. Full duplex means data can flow both ways at the same time, like a phone call. Half duplex means data goes one way at a time, like a walkie-talkie. UART and SPI are full duplex, while I2C is half duplex. This affects how fast and efficiently devices can communicate. Another key concept is addressing. In I2C, each device has a unique address, so the master can talk to each one individually. SPI uses chip select lines to pick which device to talk to. UART doesn't need addresses because it only connects two devices. Understanding addressing helps you design scalable systems. To sum up, SPI, I2C, and UART are the most common ways for devices to communicate in electronics projects. Each has its own strengths and ideal use cases. Now you know when to use each one, how they work, and what makes them different. Thanks for watching this quick guide. Keep exploring and happy building with your electronics projects.